Welcome to my presentation on how to make number theoretic transforms really fast and how to use these number theoretic transforms to accelerate TFHE-like structures, specifically final. So how do you build the fastest possible TFHE accelerator? And I'm going to explain this using factories. If you are a person designing a factory, what you want is maximum throughput, ideally for the given factory space. So your boss comes to you, he says, here's a factory, this is how big it is, fill it full of machines and get me the most throughput possible, the most things built per day possible. Which means you want to pack things tightly, very tightly, because the more tightly you pack things, the more assembly lines you can have, the more things flow through, the bigger your throughput. And so that requires some analysis, because that requires knowing like what are you trying to build. And in our case, we are doing TFHE computations. The output of our factory, of our FPGA, is blind rotations, effectively, because that's the main part of a TFHE. If you get the blind rotation right, all the rest you can handle in the CPU and some more custom thing. Your FPGA should really be built for the blind rotation. And a blind rotation, for the majority of it, is number theoretic transforms. You can put the rest of the stuff on the FPGA as well, but if you get the number theoretic transform right, that's the most important thing. What does a number theoretic transform consist of? Well, a number theoretic transform consists of butterflies. So if you then get the butterflies right, you'll probably get the number theoretic transform right, which means you'll get the rest of the TFHE circuit right. So a quick recap. What is a butterfly circuit? A butterfly circuit consists of just 3 operations. Modular multiplication, in the case of an NTT, or complex multiplication in case of an FFT, a modular addition, and a modular subtraction. And of course, the multiplication is going to require the most logic. So then we really need 2 things for fast TFHE. We need a circuit that consists of only these butterflies, because you can of course build your circuit with a lot of control logic, with a lot of routing towards these butterfly circuits, but then you're packing on stuff that isn't the butterfly circuit. From a mathematical perspective, the only thing you really need to do is the butterfly circuit. You can of course add hardware to schedule these butterflies in a certain way, and you can add the stuff, but this is overhead. This is not really things you want to do. These are things you might do out of necessity, but these are not the things you really need. And the second thing you want is these butterflies need to be tiny, so you can fit as many of them as possible. Because at the end of the day, you can just kind of express a TFHE, or in our case, a final blind rotate, as the number of butterflies you have to do. So, how do you do modular multiplication? How are we going to make this butterfly tiny? Well, this is a very well-studied problem. Especially here at CHES, but also in many other conferences. And usually people come up with, well, let's go look at, if they want to do a really good job, they look at, well, how does the modulus look? Can we work around this modulus? Can we find tricks to use the structure of a modulus, like a modulus of, say, 2 to the 16 plus 1? Well, that's a good modulus, because anything that goes beyond that 2 to the 16, we can replace by a minus 1, for example. But usually we don't get such a nice modulus. We have to like work around it a bit. And the problem is what you really get is people put in a lot of design efforts, and they end up, despite all their design effort, with something that looks a bit like this. You have a lot of handcrafting, a lot of control logic, a lot of extra stuff that you need to do this modular reduction. Now, in this presentation, I'm going to show you how do you do a modular multiplication for the cost of just a multiplication? The modular reduction you get for free. We're going to start with looking at this. So normally, modular multiplication is, you do the multiplication, you do the reduction. But, and this is what our whole thing is going to rely on, in number theoretic transform, you're not doing any modular multiplication. You're doing multiplication with a constant. If you're doing RSA stuff, well, both things that go in are going to be different every single time. If you do modulo some 1024-bit or 2048-bit number, they're different things. But in a number theoretic transform, you're doing times a twiddle factor. You're doing, if you're familiar with FFTs, that's times e to the power of something. If you're familiar with entities, that's times your triple factor. And then you do the reduction. And since these are both constants, you can see this function as a linear function, because both of these functions are linear. Multiplication is linear, reduction is linear. So, since they're both linear, you can split the inputs and sum them later. Because you consider this function where you multiply with a constant and then you reduce, as just a function of taking the first 5 bits, taking the next 5 bits, taking the next 5 bits, and taking the next 5 bits. So for our parameter set that we're using for final, we're using 20-bit numbers, and we just split it up. Okay, well, now we have to calculate 4 different functions. What does that help us? Well, it helps us because of the way that an FPGA works. And so for the people here who are not familiar with FPGA primitives, on FPGAs, you get lookup tables. These lookup tables, these are tables that you have full control over, that you can program. They come in with inputs, a certain amount of inputs. On our FPGA, on the ultra-scale devices, 5-bit inputs and 2-bit outputs. Which means if we want to create a function like this, which is a 5-bit input, 20-bit output function, we can do this by taking 10 of these lookup tables and programming all 10 to generate this function effectively. And then you can take 5 bits of input and you get 20 bits of output. And this gives you this whole function for only 20 lookup tables. Now for the people not familiar with FPGAs, 20 lookup tables, that is very small. And in fact, that's about the cost of just doing a multiplication, because when you do a multiplication, you also use these lookup tables. But now you've gotten the modular reduction for free because you've calculated the reduction while you were doing the multiplication. And this is critical. You need 4 functions, so 40 lookup tables, and then you need to add all the results together. Of course, if you add all the results together, you add 4 20-bit numbers, then you get a 22-bit number, which is not what we asked for. We asked for a 20-bit number. So then you can do some reduction, some cheap reduction to finish it. Do you really need this reduction? No, we'll show that later. But first, sometimes you might point out, well, sometimes we're not calculating with constants. What do you do then? Then we use a slightly less efficient one. Then we actually have to use a proper multiplier. And then we have to do something called K reduction, which is where you use the structure of the modulus, in our case, 3 times 2 to the power of 18 plus 1, to work around and reduce efficiently. For more information, see the paper. Now, 22 bits, they don't have to be reduced. So this final reduction in K reduction and this final reduction with our constant multiplication, this doesn't have to be done. Why does it not have to be done? Because we can take this 22-bit number and multiply it with a constant again and get 25 bits again and reduce again. And we only really have to, at the end, reduce down to 22-bit numbers. The difference between working with 22-bit numbers or 20-bit numbers for the rest of our circuit is not that big. So we can do lazy reduction and we can only reduce at the very end. And this saves us a lot of effort because then the only thing we're doing is this. That's the only logic we need. Those 4 groups of lookup tables and 3 others. That's it. So this only works if W is a constant. You need W to be a constant, else it's not going to work. But it means no multipliers. We only use lookup tables. And for the people who have been sleeping the whole time now and are like, whatever, I don't care, this is what you should pay attention to. This is the only slide you have to pay. The very brief of this whole presentation is we do modular reduction without having to do reduction part by just using lookup tables, the same way you would build a multiplier out of lookup tables, but instead of just using it for the multiplier, we do it for the modular reduction. That's it. You can go back to sleep now. We'll continue the presentation. So, end result is, or the best modular multiplication circuit out there for 20 bits until now required 136 LUTs and 1 DSP, which is something like that K reduction circuit. This thing just uses 120 LUTs on average. Why on average? Well, because the lazy reduction causes the circuit to grow very slowly. So in the beginning, it's going to be slightly smaller than towards the end. But 120 LUTs on average. Which means this is just cheaper than... You lose the DSP and you use less LUTs. But now, of course, we've done a thing that none of the other circuits have done, which is we've required our W to be a constant. We've required our twiddle factor to be a constant. And for a lot of circuits, this will not work, because for a lot of circuits, you need to fill in. You need to fill in your twiddle factors during runtime. Why? Because we only have one butterfly circuit and we feed data to it. That's how it's generally done. In our case, we're going to put the circuit on there, and we're going to have to do alterations to the data to make it work. Or, alternatively, we can just put the whole entity on. Like the previous speaker did a full FFT. He put the whole thing on. We are also going to put, we could also put the whole thing on. But this is a bit tricky for FHE parameters, because on FHE parameters, you're not working with an N of 128. Like the previous speaker, we're working with an N of 1024. With 10 stages, 1024 times 10, even with our tiny butterfly circuits, that's too much. If you would do that with ORs, you would fill the whole FPGA with just one entity. And we need 8 of them to get the maximum throughput. So that's not possible. What we instead do is we kind of fold the entity on ourselves. What we do is we do the following. So we use the fact that any entity can be seen as a matrix multiplication, and that you can sort of split this matrix into its vectors parts. So you can take your 1024 and you can split it into 64 times 16. And so what we do is we first do an entity of size 64, and then we do 4 entities of size 16. Yeah, sorry, that's my phone. So, how do we then turn this into final? Well, the final algorithm consists of, is kind of like the TFHE algorithm, but with a couple of changes. Mainly, it uses a much smaller bootstrapping key, which can be really nice for FPGAs, because on FPGAs, the cutoff for your internal memory is around 24 megabytes, 40 megabytes for the bigger ones. And so if your bootstrapping key is small enough to fit inside memory, this saves you all the hassle of creating a really efficient streaming memory interface. Can you make this streaming interface work without being memory bound? Yes. But not having to do it is a nice thing. You'll still have to, of course, feed in the bootstrapping key, but it means that you can reuse this bootstrapping key over and over and over again without having to reply back. The other nice thing is 20-bit numbers rather than 32-bit integers, which definitely saves on the butterflies. It is, depending on what parameters you take for TFHE and parameters for final, sometimes a bit more computationally expensive, sometimes a bit less computationally expensive. If you just take the basic parameters, final is better. If you take very specific parameters for TFHE, like the FPT paper did, TFHE can be better in terms of the number of butterflies that you need to do. This depends on choices of parameters. But in general, for normal parameter sets, final is nicer to work with as a hardware design. Further advantages, well, so like the 20-bit number, it fits, and very important, it has a simple open source license-free implementation that you can just get. The final, but intended, hardware accelerator looks like this. You have your CMUXing circuit where you choose between the different polynomials. You have your big external product with your 7 entities, one inverse entity to combine all the things, and a final addition. Run through this 610 times. Everything is pipelined. We work with batches of 32 ciphertexts, so the whole thing is filled at all times. This, of course, reduces the latency a bit, but it means we can work at a very high frequency of 305 megahertz, and thereby get the highest throughput reported until now in literature for FPGAs. Yes, and this was mentioned. So these are the current results. Are there any questions?